so far we try to give the inputs which are not same as the training data for testing data, and we could find that the machine can come very close to right the accurate answers, right? It can actually make a proper decision based on this. Now let's do the analysis, right? What exactly has happened, I'll try to show you. Okay, so now let's consider the outputs and the inputs one by one, and let's just check what exactly has happened. So the first one is like this. So in the most recent classification, uh, the machine tried to classify in the following fashion. Okay, so my test data is like this, and it is actually classified that as with 96% of confidence. It told that this is something like 4, right? So the classification, the test data is on the left side. This is given to the machine. Machine's answer is this, right? So the output is like this: 0.01, right? 0.002, 0.0017, 0.9666, 0. So you see that this is actually being classified as number 4, right? That was the first. All right. Then the second answer, right? We try to give a value which is closer to 2, but not exactly 2. So when we trained, we gave the 2, right? And when we are testing now, we gave a different representation. So let's see how the result came, right? So this is the second data, okay, which I try to give. Now we can see that it's not 2, right? But it can be, right, assumed to close to 2 because only this one particular, right, location, there is a difference, right? So you can see that the confidence level is 9936, 0.9936, 99%. So, right, it tried to classify that accurately, right? Then let's go to the third data. Third testing data was closer to 3. So this is the third data, right? So it is pretty much closer to 3, and the machine could recognize that. Now, what uh, what else we can try to make? Now, if you compare the second and this third image, difference is only 1 pixel, right? Only 1 pixel difference is there between the two of both the test data, only one. But how could there be a difference? Such a tiny difference results in two totally different classification, means you can understand that machine had paid so much of attention during the learning process, correct? So you see just 1 pixel, right? Human might make an error, but machine's learning is, right, pretty much close, pretty much accurate. That's what we can understand here, right? uh, the training data, right, uh, for these two classes, like you can see the number 2 and 3, right? If you look carefully, only 2 pixel difference overall, right? So it means such a tiny information also being used by the machine to learn something. That's what is a very important thing that we can understand here, right? It's not that machine will learn only if right a huge amount of data set is given. Even there is a minute detail, right, available, means machine is going to learn that very neatly and right responsibly. Okay, so it's actually it's a very amazing fact that the neural network catches such a small difference and applies that, right, whenever it comes to the practice, right? Whenever you ask machine to classify something, it's going to classify, right, by using such a small information that it has gained during the learning process. So this gives you a very clear idea that how detailed is the learning process, first thing. And what all machines do learn, even if there is 1 pixel difference, right? Only one bit is different. right? That is also going to be considered over. Okay, so let's look at the fourth class, right? So in the fourth class, actually machine had some confusion. We actually have observed that. Let's see. Let's do the analysis of that part of the result. Okay, so okay, let me go to the fourth. Okay, this is the next. So the input is something like this, right? So I can see that the machine or the neural network classified this as 5 by 47%, right? 0.4712, 47% of the probability, right? At the same time, it also says that this could be 3 with a 32%, okay? Right? 32% says that, okay, this could be 3. Now, what exactly has happened? Can you guess? So you see that the input image appears like a squeezed 5, right? 5 has been squeezed to get this data, right? But what exactly happens is that the neural network finds some of the horizontal lines that are that has some resemblance with the features of 3. You can see that, right? The 3 says that there are 3 dots which are here. Actually, that's also there, right? Again, at the center you have 3, right? 3 dots. Again, I can see the 3 dots here. Again, the last line also has 3 dots. That's also there. So it's some resemblance. May not be that good. That's why it says that it's not very confident. It simply says that 30%, right? There is a chance that this is 3. But definitely there is more resemblance to 5, right? Because of the other 2 dots, what it actually observes over there. Because of that, it actually finds out that 47% chance is there. This is the 5. Okay. So now the idea is that it is not very confident. That's the first thing, right? Maybe the training is not sufficient. If you are going to give a 5 like this for the testing, you should try 5 with this kind during the training as well, right? Machine will learn more. Right. So in order to get higher accuracy and the performance in these kind of cases, you need to increase the training, right? So give more varieties of training data so that the machine can understand, machine can identify. Okay. So let's move on to the last case, that is the fifth data set. So the fifth one was also pretty much closer to 5, but not exactly 5. And this is how it was looking. Okay, so this is the fifth image, and we saw that this is getting classified into 5, and there is 98% confidence, right? It's definitely, it's no wonder that what we see in the input image is exactly right, pretty much closer to almost identical. But I can come back, I can show you with, I can actually make a comparison with the fourth image, right? So which you can see on this actually is pretty much closer to my fourth data set. Only 2 pixels are different. There are 2 additional pixels. One is on the top and one is on the bottom, right? So that actually, right, by just adding 2 pixels, you can see that it is increasing the probability or the confidence of the machine making the decision that this is 5. All right. So a very small this thing. So now you see that, right? These this is how, by just adding a very little bit of information, right, helps us machine to make a proper decision. That's what is the overall understanding from this particular experiment what we do, right? So initially we try to give the data that is corresponding to the training and the testing same, right? We saw that, okay, 100%, right? Result is 100%, everything with confidence machine classifies. But when you try to alter your input images for the testing process by slightly modifying, slightly bringing some differences compared to what is there in the testing training data, you can see that this is what is going to happen, right? machine's confidence is going to vary depending on what type of data I'm trying to. If it is close enough, right, you will see that 90% plus for sure. But if it is right, if you bring a lot of confusion over there, right, then there will be something like 40 to 50% confidence, right? The confidence bring is brought down by that much amount. All right. Okay, let's move further. So this is all about the neural network and the multi-class classifications using neural network, right? So you can try to build your own what you call classifications like this, but I just want you to do one thing and share me the result, okay, what you obtain, right? Or even if you can share me the code, right? I want you to, instead of classifying these numbers A, B, C, D, sorry, 1, 2, 3, 4, 5, right? This could be something like a homework for you, okay, right? So this is a homework task. I want you to solve this and take some time. Maybe by weekend you can share. Okay. Right. So this is the one. So uh, write a code that you should train and test. Right. The letters now instead of numbers. Do it for the letters. Okay. So I want you to classify. Right. A, B, C, D, E, F, G, 1, 2, 3, 4, 5, 6, 7, and H. Okay, this is what you should train the machine, right? And the testing should be done in two phases, like what we did earlier. It's exactly same, only the data you should change and write some modification in terms of the size of the neural network you might have to change, because it may not be sufficient to define only 5 into 5. Maybe you can go for a 7 into 7 image, right? So every image should be 7 into 7, 49 pixels, not 25 pixels, right? So just remember, right? So this is the training data. So 7 into 7, right? This is the size what we are specifying. Then testing should be happening in two cases. The case number one, same as training data. Okay. Then the second one is, right, different. Different than training data. Right. So I want you to do this as a hands-on session. Do it and right, share me the code by Friday or Saturday. Okay, so let's keep it Saturday. No Friday. Saturday I'm expecting this code. All right. So implement that and right. You can ask me help if you want anything, any help you want before that. Right, before maybe Friday session, you can ask me down related to this. But Saturday I'm expecting an output from this. Okay, a code completely this. So the fundamental codes I'll share you today, right? Whatever codes we have written, right? So for the previous class, I'll share. You can use it as a reference and build your own code. Okay. So let's move further. So again, there are multiple examples I can give, but as of now, I just want to go ahead. And we are moving on to the next concepts of machine. The Okay, we finished actually the machine learning using the artificial neural network. Networks is over. I'll slightly move further, right? I'll move on to the deep learning. Right, we are very close to our actual concepts, right? So the project is actually dependent on this. So fundamentals of the projects you already know now. What are they? Let's move on. So deep learning is a machine learning technique that employs a deep neural network. So my intention is that I want to change the neural network architecture and I want to bring in, right, the deep deep neural network. So deep neural network is a multi-layer neural network contains two or more hidden layers. What do you mean by deep neural network? Right? DNN, right? Has two or more hidden layers. This is the point. Okay. Now, uh, it might look like very simple, right? So, okay, I had one hidden layer in my previous case. I'll simply improve. I will improve upon my circuit or the architecture, and I'll put two hidden layers, right? May look like pretty simple, right? But let us look at what exactly is going to happen when I move on to the deep concept of deep learning and how it is related to the machine learning. Let's see. I'll try to put a diagram so that we can understand this. Right. So you can see that uh, it's a training data. There is a learning rule. It is connected to the deep neural network. So that is this part. This part is considered as a training part. And then we move on to the testing part where we have input data is assigned to the deep neural network and you provide it provides you an output, right? So what's the difference? So the deep neural network lies in place of the final product of the machine learning. And the learning rule becomes the algorithm that generates the particular model. So what is the difference we observed, right? You can understand that in case of a machine learning, so the deep neural network was not there and you had the machine learning algorithm. So training data was given to that actually created the model. And rest of the things are same, right? So you didn't had a learning rule over there, it was an algorithm. So now you see that we have a learning rule coming into picture which helps us in the optimizing the weights of the neural network. So you get a deep neural network getting trained. So rest of the part remains same. Input is provided. This is a testing phase, right? Neural network evaluates that input by doing the calculation and provides you an output. Okay, right. Now we know that the deep learning is just use of deeper, or we can say that more and more number of hidden layers in the neural network. So now definitely there is a question that might arise. I had one neuron, single hidden layer. It could work fine for me, right? Then why the deep neural network is so at becoming so attractive when it is actually having more and more number of hidden layers, which actually making things complicated, right? Weight updation needs a lot of time, right? There is a lot of calculation, many weights, right? Maybe you have some issues with the what you call in deciding which learning rule, what activation function, etc, right? Actually this is becoming more and more complicated now when you try to increase the number of hidden layers. But why it is being so attractive is the question, right? So let us look into what exactly has happened in the overall life of a neural network, right? So it was designed maybe 20, 30 years ago. Then what exactly happened? If you look at that, you will get an answer why the deep learning or the deep neural network is so famous, why it is so attractive. You will come from. Okay, now uh, let's say there is a first what you call, I'll call it as a first generation, right? So maybe 30 years back, right, approximately, right? Using the fundamentals of mathematics, right? People developed the first generation of a neural network. Whenever, right, they're trying to solve very simple problems. Okay, now later on, it's like very simple problem, like simple and gate or gate or something. Later on, they identified that yes, there are problems. which are non-linear in nature. They identified that okay, neural network, single neuron can solve only linear, like what we studied. Right? When we solved, when we began, we were using only single neurons. Later on, we identified that okay, this is not going to work. Right? Whenever I have the situation wherein I have to solve a non-linear uh, problem, right? Then definitely you have to uh, use the use multiple neurons in the same layer. Okay, so a they added one particular neuron. So neurons, there are multiple neurons came into picture. Then the problem became slightly complicated. Then you couldn't use this single layer, you had to extend it to a different layer. Okay, so maybe input layer and output layer when there was one input layer and one output layer, that itself suggested that okay, if you improve the number of layers, you can solve the problem in a much easier fashion. Okay, so that was the idea. Later on, right, the training of a multiple layered neural network, right, was solved by using what is called as a back propagation algorithm. This was again around 25 years back. All right, so this was they introduced what is called as the back propagation. And right, whenever the back propagation was introduced at the beginning, they never worried about what how much is the calculation that is happening, what is the number of multiplication, number of additions that is happening, or what is the complexity of that algorithm. Nobody worried. But later on, right, there was an issue that is related to the complexity. Right, the complexity in the sense, right, it is directly related to the performance of the practical problems. Right, so the right, definitely in order to overcome, right, those issues, you had to increase the number of layers. Okay, so they brought more and more number of layers in place. Right, but for a back propagation algorithm, simply keep increasing the number of hidden layers, things make things more complicated rather than reducing rather than giving you a solution. Okay, so the problems were not simplified, problems were increasing. So right, if you have a back propagation simple neural networks, right, you try to increase the hidden layers, no, it's not working. Right, so the performance was actually more and performance was becoming more and more poorer when you were trying to increase the number of hidden layers, and the back propagation algorithm was being used. Okay, right, later, maybe 10 years later, like maybe 15 years before, 15 years earlier from current situation, what happened was, uh, the concept of deep learning was right brought into picture. Deep learning was not implemented. Okay, the concept came into picture because normally the trend is that theory comes almost 10 to 15 years earlier than the actual implementation. Right, so we know that deep learning is being implemented in last 5 years now, but this concept was brought around 2000 to 2005. Right, what exactly happened was, so they try to design the hidden layers such that it should be able to solve the problems of training, whereas the performance, right, in terms of the complexity should be as simple as possible. You just have to keep it as simple. Right, sufficient performance plus reduction in the difficulties in the training process. Okay, so this is what was the idea. Theory was there, but hardware was not there. There's no good hardware, no good GPU to do that job. Right, but nowadays you see that it can be implemented because the hardware industry supports very well for the software requirements. You have GPUs very fast. Right, so because of that, you have uh, the neural networks taking over the machine learning techniques and becoming the deep neural networks, and they are being implemented now. Okay, so right, it was not just a reason that you originally simply you started with this, you keep on increasing the number of hidden layers, it means it is good. It's not like that. Right, so when you change the neural networks into deep neural network, there are several changes which you need to do. right? You cannot use the same activation functions. This is just an example. I'll show you, I'll justify that later, right? The same activation function which we are using in the neural networks, you cannot apply. You have to change, right? Because if I use the same thing, right, you are actually increasing the number of number of additions and multiplication, thereby increasing the complexity of your algorithm, basically. So that should not happen, right? Something you need to do, you have to increase the number of layers, so that, right, performance increases, accuracy increases, complexity reduces. All right. So overall, you can say that, right, the additional hidden layers, right, resulted should result in improving the performance, not like increasing the hidden layers in the back propagation algorithm made the result more and more poor. It's not like that. You should have some more changes. Okay. So let's directly go to that concept now. So what exactly has been improved in case of a deep neural network? Okay, so this is the next topic what we are going to discuss now. So improvement of deep. All right. So now the reason that a neural network with the deep layers yielded very poor performance was, right, the when I increase the number of layers, I am expecting more and more training data, right? So if you increase the number of hidden layers, there are more weights. More weight means for updation of those weights, you have to give more time. But you see, just now in the previous example, when I was running the code, I was not patient enough to look at the result. I just gave the number of iterations or epochs as 1 lakh. I couldn't wait, right? So this is something like, you see, you have to give that much time so that the machine will learn, right? So when I increase the number of layers and I'm not ready to wait, means I'm not ready to give enough time for it to learn, means there is no meaning in that, right? So it machine is not going to learn. There is a poor classification. This is what was the result. In case of a back propagation, increase the hidden number of hidden layers, make more and more define more and more weights, right? But later on I'll say that, okay, performance is poor because I never trained it sufficiently, I never give enough number of data, right? So this is the problem. So when it comes to the neural network, right, why the result was poor in case of increased number of uh, neurons in the hidden layers, or the increase in the number of hidden layers, basically, right, is that not training the neural network properly, right? So if you remember, the back propagation algorithm experiences, right, some of the very fundamental problems, right, whenever the number of hidden layers increase, right? So let me write that one point here, right? So artificial neural network with deep uh, deeper layers, I'll write deeper yielded poor performance, right? This means what? What do you mean by this? What is the indication, right? This means training was not proper, right? Could be something like you didn't had uh, the sufficient hardware for that, right? The machine was not the machine, in the sense the hardware or the platform on which you are trying to implement that is not capable of doing that much of training. First case, right? Hardware is not supporting. Second thing, even if hardware is that, it might be very slow, right? It might be taking like 2 3 days for doing one training of say 100 iterations, means, right, definitely nobody will use that. That's the second reason, right? So overall you can see that the training is not proper. I want to add another point. Maybe you didn't had enough training data, right? Data was less, right? Hardware was not supporting. Even if the hardware is supporting, it is slower, right? Because of all these reasons, right, we can say that the training was not proper. Simply by increasing the hidden layers will definitely not help. It is going to make things more complicated, because more uh, what you call weight is more weights are there, right, for each of the neuron in each of the layers, which needs more and more time, more and more iterations to make them understand the problem properly, or so that they can make a proper classification. It takes more time ultimately. So overall, whenever they are not classifying, it means there is some problem with the training. Right. Later on, they try to analyze what exactly is happening. Why machine is not learning, right? Though I try to increase the hidden layers. So original idea was that, okay, a problem is not being solved. Increase the number of layers, it will solve. Because more and more non-linear functions are being brought inside there, so that the machine will classify. This was the idea. But later on, when they try to analyze the situation, what exactly is happening here, why it is not being solved, right? So they could understand something more, because till then the most common algorithm used everywhere was something like this one, the back propagation. All right, propagation was the one. So let's talk in terms of back propagation, right? uh, the common training rules, such as EBP, that is error back propagation, right? Uh, they experience some of the difficulties when the deep hidden layers are in place. So as I told, the original idea was, if you are not able to solve a problem in neural network, increase the hidden layer size, right, so that it will solve. But actually they observe that the most common algorithms, such as error back propagation, right, etc., are giving you poor and poor performance when you increase the number of hidden layers, right? Later on, they try to analyze what exactly is happening, right? Right, it might have taken a lot of time to do this job, like tracing out where it is missing. Something is missing. Weights are not getting updated properly, right? Weight updation is happening, but it is not proper. Ultimately, after doing hundreds of or thousands of epochs, you see that it's not getting trained properly. So what could be the possible reason, right? Whenever they are trying to trace it out, right, they could understand that the EBP, right, is actually experiencing some difficulty, right? EBP is suitable for only those neural networks which have very less hidden layers. When you increase the hidden layer size and when you bring the deep neural architecture in place, right, there are three major problems, three major difficulties. Okay, so let's see one by one. So the first difficulty right, is called as the vanishing gradient. So because of this only, we have a different type of representation and different types of calculations, activation functions, right? Weight definition comes into picture when you are dealing with a deep neural network. So that is the difference between artificial neural network and the deep neural. Okay, so let's look at this. Now, let's consider that there is a delta value in case of the back propagation algorithm, right? So the vanishing gradient in the training process with the back propagation algorithm occurs when the output error, right, is more likely to fail to reach the further nodes. For example, let us try to understand the vanishing gradient concept, right? So vanishing gradient, I'll write the point first. In case of the training, in case of the training process, with the error back propagation, it occurs when the output error fails to reach the further nodes. Okay, right. Now, the idea is this. Say, if you are considering the error back propagation algorithm, neural network gets trained, right? What is the fundamental idea in training of a neural network and using error back propagation? You consider the output error, make the error to propagate backwards, right, towards the node which is before the node which you are considering, right, before the layer. So if at all that is a hidden layer, you train that, right, get the error over there, convert that into delta, make use of that delta to calculate the error of the layer previous to that. Okay, and keep repeating this until you reach the first hidden layer. All right, so the neural network had maximum two hidden layers, let's say. So in that case we don't see this issue, but when it becomes deep neural network of 100 layers, you see this problem. What is the problem? I'll try to show you with the example, with one diagram. Now we know that we have the output error, right? So you will call this as uh, I think we denoted that as E, right? So I have error E here. Okay, this error give rise to the delta of this particular layer, which is the output layer. I hope it is fine, right? Now this delta will be used to calculate the errors over here, right? So this will be the delta, maybe I'll call it as delta dash, right, E dash. Now, right, you have many layers like this. You can see that there are dot 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 indicating that there are many such layers. Now, as you propagate from output layer backwards towards the hidden layers and the layer before that, you will observe that this delta reduces, right? Because the final error is nothing but that is the accumulation of all the errors of this layer. So error before that will be much lesser than that, because all of them added together to get the errors of the next layer, correct? So error will keep on reducing, right? So error keeps on reducing means what? The delta values will also keep reducing. So you see there is an equation, right? If you want to add, if you want to calculate the updated weight, what is the equation? Updated weight is equal to, so I can write wij is equal to old value wij plus the delta wij, isn't it? Where the delta wij has to be alpha into delta I into xj. So you see, at a particular layer, what happens is that there is no change. It says that the weights are not getting updated because the delta becomes equal to 0. Delta keeps on reducing, after some point delta becomes 0. So when this delta is equal to 0, what happens? Delta ij becomes equal to 0. That means this wij, delta wij becomes equal to 0. So old weight is equal to the current weight, right? Old weight itself will be used as current weight. No, there is no weight update at all, right? Now you are able to understand that, okay, this is why the weights are not getting updated. Machine is not learning. So initially, definitely you will see that, okay, these layers are learning, weight is getting updated because there is at least a small value of delta coming into picture. So this delta itself is the gradient, and gradient vanishes as you increase the number of hidden layers by using the back propagation algorithm. Very major issue. Okay, so this is what is called as the vanishing gradient, right? So we know that the back propagation algorithm trains the neural network as it propagates the output error backwards, right? So error hardly reaches the first layer or the first hidden layer. So the weight cannot be adjusted, right? So the hidden layers are close to the input layer are not properly trained. So what is my conclusion because of this? Due to the vanishing gradient, this implies those hidden layers close to the input layer are not properly, right? So now you see, once this happens, even if you increase any number of hidden layers, is there any effect? There will be no effect, because I keep on increasing the hidden layers, but the weights are not getting trained at all, right? The delta value is not getting updated, so weight will not update. So there is no meaning in increasing the number of hidden layers. This is the first point which they identified, right? When they tried to explore why the machine is not learning when you increase the number of hidden layers, the first solution they obtained is this. Okay, right. So in the next session, right, we will see what are the other reasons why the machine is not learning.